Welcome to this conversation we're about to have on 10 reasons to do FMEAs and FMECAs with AI. Now, AI is a very powerful tool, we know this, but it's also a buzzword, and it's sort of being introduced into the world of reliability engineering. But I'd argue that we don't really know yet how to do it properly. And one of the first things you need to do when you have AI injected into your reliability engineering activities, including FMEAs and FMECAs, is to not forget the first principles. So if you're interested in listening to me to try and find out how AI can do FMEA or FMECA for you, then this is going to be a long hour for you, because I'm not going to advocate for that at all. So I'm going to talk about 10 reasons to do FMEAs and FMECAs, which are going to be very relevant for people who want to do FMEAs and FMECAs without AI. And we'll talk about how to make that work with AI throughout this conversation. Now, one of the common things that we start with many reliability engineering courses and lessons is we try and scare you guys into submissions, say, hey, here's an aircraft crashing. That's a very bad thing. And then we start launching into often measuring reliability or discussions on how to analyze reliability, both of which can be very important. I'm not suggesting anything else. But if all we're doing is statistics and data analysis, we're just admiring a problem. FMEAs and FMECAs are a little bit different. They're not there to be super quantifiable. They're there to help make sure that we make our things reliable, because measuring or analyzing is nowhere near as important as actually making your product, your system, your machine reliable. And that's what we're going to be talking about today, and how that applies to a quality and reliability mindset. Now, I'm going to go back to the concept of AI with this little diagram here, and you should be able to see a large grey rectangle on the left and a small orange square on the right. And got a little scale there to show how much bigger that grey rectangle is. Now, this is the area of design where AI can accelerate everything. Let's call this the common design space. And that means that AI can help by going back to things like requirements, published literature, proven components, standards, known architectures, previous models, etc., 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 to help accelerate that common design space. But it's the last 10% that is essentially the difference between an amazing and a mediocre product. This last 10% is something that AI cannot help us out with. And if you want to challenge me to that, say, hey, AI can do absolutely everything, then all you're doing is arguing that you don't need a job. If there are no doubt going to be certain things that AI can do entirely, so to speak. And we've seen some amazing things that AI can do in terms of, for example, video creation and just generating videos from prompts and directions. However, we are yet to have AI generate an Oscar-winning movie. And the reason is because AI can help regurgitate. Humans are all about imagination. So AI's regurgitation, which is not trying to downplay that at all. That can be immensely useful, immensely helpful. But humans are the only things that can still do the imagination thing. And that's important, because that last 10% is with the new features, the edge cases, how humans behave, where failures hide, etc., etc., etc. And of course, interfaces. AI can help us out with interfaces, but it's the human imagination which understands how systems interact with the world around it. And essentially, this is where we need to think. So a lot of people have been swept up with this whole idea of going, look, AI can do so much, therefore we don't have to do anything. That's not true. It's made AI can help make our life much, much easier. But if you think AI can do everything, then all you're going to do is quickly produce a mediocre product, the stuff that everyone knows how to do, because AI will regurgitate that common design space. It's the last 10% that is the separation between an amazing and a mediocre product. And we'll talk about how we do that for FMEAs and FMECAs and actually all reliability engineering activities. And we're going to do that by going through 10 reasons. They're my 10 reasons, my favorite reasons, and they're on the screen right now, and there's a lot of words there. but we'll go through them one at a time, starting with no complex, expensive fixes. And veterans of my webinars are going to remember or recognize a few of the things I talk about. And the reason why I talk about these things a lot is because it's common principles. No complex, expensive fixes. Shouldn't we want that all the time? Yes, we do. And there's only one way to do that, and that's by finding failure modes earlier. And AI can help us do that. Just be very, very clear. Trying to understand how your thing can fail before it becomes locked in a design that is very expensive and challenging to modify. So for example, let's look at my central system that I use in a lot of my discussions, the smart lock. When I talk to people about FMEAs and FMECAs, what's their biggest pushback? You want me to do a FMEA or FMECA before we've designed our product. How can we do that? How can we do a FMEA or FMECA when we haven't designed our product? Well, let's just say you're in an organization, a startup, that is going to build an amazing new smart lock to challenge the existing smart lock marketplace. You might recruit a ton of really smart, really useful people who have individually the skills you need to make an amazing smart lock. So we have never built a smart lock before. But that said, before you even pick up the first AutoCAD pen in anger, we know that our smart lock's going to have 17 components, 16 of them will be different because there's 2 identical handles or very slight variations thereof. Before we start designing, we know that the heart of our smart lock will be an electric motor, which turns a gear set and is controlled by a printed or printable circuit board. We don't need to design a smart lock to know this is what the heart of our smart lock will look like, even if the ultimate design means having the electric motor mounted vertically versus horizontally. That's not the point just yet. Now, the example I always use, because I've seen so many allegedly mature products have this particular problem, let's think about the effects of door slams on these solder joints which connect the cables from the PCB to the electric motor. Easy thing to overlook, especially when you have the term smart in the product you're making. Why is that? As soon as it's smart, we get enamored with functionality and tend to step over the really basic things which would absolutely destroy your product's ability to do what it needs to do. And we know that whether we like it or not, smart locks will be installed on doors which will routinely be slammed by the weather events, small children, marriage, you name it. It's going to happen. And if our smart lock fails because these solder joints fracture for every door slam, then we are going to go out of business very, very quickly. And solder joints aren't strong. The main purpose of solder is to conduct electricity. So there's no reason why we can't think about this very obvious issue before we start designing. And if we do that before we start designing, let's think about some wonderful ideas we can incorporate into our very first design. So, for example, we might choose to use thicker gauge wire to provide more contact area with the motor terminal. We might make sure those wires are shorter to accumulate less momentum and have them secured to the chassis. We might have a socket and plug instead of a solder joint on the PCB, which also makes assembly much easier. And that socket and plug also helps us minimize wire length because we don't need to have that excess play to allow someone to solder it. Now, if we think of these ideas up front, they are all fast, simple, and in quotation marks, free. Now, some of you might be saying, well, hey, those clips aren't free. That wire is a little bit thicker, so it's going to be more expensive. And you're right. From a very legalistic and overly technical perspective, there is some cost with these changes. However, if you put these into your first design, the corresponding cost increase associated with the overall production costs of this smart lock is going to be so small that it's practically zero for a decision. That is, it's so small that it should not stop you making a decision to which might improve reliability remarkably for your product. And when you do this, when you have this mindset up front, this quality and reliability mindset, you have this robust, reliable design from the very start. And when you have these robust, reliable designs from the very start, your production process becomes so much more straightforward because you are not constantly putting functionality into your device, you're not constantly putting robustness into your device that your first design did not think of or did not incorporate. Which leads me to the next reason: no complicated equations. When you do a FMEA or FMECA, you might have noticed that so far in this discussion, we have not had any reference to the Weibull distribution, normal distribution, pi, square roots, anything. And that's a very good thing because at the heart of design is imagination. So I'm going to introduce you to a character, one of the three enemies of reliability that I like to illustrate. The first one is the ponderous professor, who is often the person saying, hey, that airplane crashed into the ground, therefore reliability is really, really important. And when I say really, he means really, really important. And this is pretty much all he has in terms of motivation, because this guy, for whatever reason, gets excited by analysis. And he needs to justify his existence by somehow linking all this analysis he wants to do to an airplane falling out of the sky. So once we have the scare campaign, we'll start to see all sorts of equations and charts and everything else. But the problem with this is that he is not interested in FMEAs because they involve subjective assessments and not years of painstaking data analysis. Some of you might know this person. I've met a couple of these over the journey as well. And FMEAs are not interested in doing exhaustive analysis. FMEAs are all about finding those fast, simple, and free corrective actions. In fact, we aren't interested in having a direct correlation with every corrective action and a potential root cause. For example, if you can imagine 30 fast, free corrective actions, and it turns out only 5 of those extend or improve the reliability of your product, but you didn't know which 5 of those 30 were the ones that you should introduce. Well, because they're all fast, simple, and free, it doesn't matter because you've had the chance to upfront, because you thought about these things early enough. There's no cost, there's no delay associated with putting 30, 40, 50 smart ideas into your design. If only 5, 10, 15 of those end up improving the reliability of your product, that's fantastic. But it might take years, hypothetically, with this guy to work out which one of those 5, 10, 15 would have done that if you're trying to predict that upfront. You don't want to do that. You just want to think of as many fast, simple, free, good ideas up front, put them in there, which will all but guarantee you'll have remarkable improvements in reliability. So we're not interested in ponderous professors or complicated equations at all. He is one of the biggest enemies of reliability. He will not help you answer the question, what do I need to do to make this item reliable? He'll give you perhaps a very specific answer 3 years too late. Now, there is a role for the ponderous professor. Do not get me wrong, when we do have failure data or test data or accelerated live testing data to go through, but that is a very targeted requirement in our production process. And when we do FMEAs or FMECAs with or without AI, FMEAs help improve thinking. It's not about mathematics. For me, it's all about that beautiful human imagination as it comes to design, which leads us to the next reason to do FMEAs and FMECAs. It makes your first design a reliable design. And people don't think that's possible. Some people don't. Many people think your first design is just a proof of concept, just to show that things can work. Well, experience has shown reliability professionals over the years that that is not the case. The whole rush to make a working prototype versus a reliable prototype is not ideal. So for example, when you have your first prototype smart lock, you do not want it to look like the one on the right, as we are seeing right now. And this is what a lot of prototypes tend to look like. They're sort of cobbled together. They have tools instead of components just to allow people to operate it. Do you want your first prototype to look like this? The answer is absolutely not, because the rest of the production process involves undoing the design that got you there. Proof of concept is great, but if you make your first design a reliable design, and that does take a little bit more time, all of a sudden, the rest of your production process is building upon something that's already on its path to be amazing. The one on the right is at best on a path to be mediocre. But we can get enamored by rushing to make these prototypes. And that can be a huge problem. For me as a FMECA, it's all about avoiding that particular problem. So we don't want to have prototypes like this one at all. And I've seen plenty that are analogous to this poor old smart lock with a ratchet on its handle, ratchet for its handle. And that leads us to the concept of the quality and reliability mindset, which I tend to represent with this light bulb icon here. And it's about trying to find and constantly looking for reasons your things can fail. It doesn't mean you need to do everything about, you don't need to address every single one. If everything's important, then nothing's important, but you're constantly on the lookout for reasons your thing won't work. Which leads us to the second enemy of reliability, the person I call the infant manager. And when he's talking, it sounds like there is a constant money bomb, so to speak. He is always talking as if we don't get to the next milestone really, really quickly. Bad things, costs, blowouts, delays, it's very, very bad. So we need to rush that next milestone. We need to get that next prototype up there, regardless of how bad it looks. Now, his favorite phrase is WTF, and everyone in this room knows, or this webinar knows, that WTF stands for I want the wrong thing fast. I want the wrong thing fast. I dare say some of you might know some infant managers out there. They don't truly respect the design, engineering, manufacturing process. They're all about demonstrating progress from a systems engineering or a project management perspective. I'm not having a go at either of those two disciplines. When done well, systems engineering is great. Project management is great when done well. But when you have these charlatans who just want to demonstrate progress and they don't care about follow-on effects, you get this concept where you quickly develop the wrong thing fast. And AI can really help us challenge early assumptions before designs are locked in. In particular, AI has no emotions. Now, usually that's a bad thing, especially in Hollywood movies, but AI doesn't care if it upsets any apple carts. So AI can help put things forward, challenge assumptions in a way that perhaps you or I might not be very comfortable doing if our infant manager boss is in the room. If AI says, hey, I don't think this is going to work, or hey, I don't think we should rush to try and get these things done, or hey, I think we should get these corrective actions done before we make that first prototype. Well, at the very least, it's in the conversation, and it's up to the infant manager to bluster his or her way through it, or hopefully have to defend it in a way that cannot be defended and relent and let us do let us have the right, most optimal production process. And when we do, it leads to saving lots of time and money. Let's look at that in greater detail, focusing on an academic study on a liquid fuel rocket engine. Now, this study looked at organizations manufacturing liquid fuel rocket engines and started with trying to understand their design time. This is actually their production schedule. And so they looked at two different groups of organizations. One, we'll talk about later. Second, we'll talk about even later after that. But they tried to characterize these different groups or categories of organizations based on design time and the cost per unit time associated with developing their liquid fuel rocket engines. Now, liquid fuel rocket engines are, from one perspective, beautifully simple. There's not a ton of components. From another perspective, they're immensely challenging because of the energies involved, the alloys that need to be used to deal with the high temperatures, the stresses, the timing, you name it. So from one perspective, they're very simple. From another perspective, they're very challenging. Now, the first category of organizations this study looked at were the organizations who rushed to build, then test, and then fix. And so they tried to characterize their efforts in both time and cost. And so for these organizations, the initial raw design effort is represented by this red hump on the bottom left-hand corner. So that's the amount of time and money spent in creating their first design. This second shape represents the time and money spent on engineering support. That is turning that first raw design into something which can work, which is manufacturable, which is reliable, which is transportable, which is aesthetically pleasing, and so on and so on. This shape on the right represents the certification resource bill, and this monstrous shape represents eliminating failure modes and mechanisms, i.e. fixing preventable problems. And this should make sense. If your strategy is all about building and then testing and then fixing, by definition, you are scheduling, budgeting for a lot of reactive redoing of stuff that could already have been done. So the study then looked at the second category of organizations, ones which had the quality and reliability mindset, where they were constantly looking for failures and failure causes. Now look at the overall resource bill. You can see that these mounds are much, much smaller, except for one. That is the first raw design effort, maybe twice as long and twice as expensive compared to the amount of time and effort that the organizations rushing to build, test, fix were willing to invest in their first raw design. But have a look at the follow-on effects. Engineering support, very, very small. And that's because the first design is close to the final, is much closer to the final design. It doesn't have to be reworked or redesigned because they made the first design reliable, manufacturable, transportable, and so on. Secondly, certification is now much simpler. Now, why might that be the case? Well, when you use the quality and reliability mindset, you know what the residual weak points of your liquid fuel rocket engine are. And so those are the only things you need to test for when it comes to validation and verification. And of course, the amount of time and money spent eliminating failure modes and mechanisms is correspondingly small because we tried to have those fast, simple, and free corrective actions in our first design. So there's always going to be a requirement to eliminate failure modes and mechanisms from our design as we keep going. But when you make your first design a reliable design, the amount of effort needed is incredibly or vanishingly small. And so when you compare the overall resource profiles, using a quality and reliability mindset turns out to be 73% less expensive in the scope of this study. It involves having design time slashed by about half, and almost certainly results in these cheaper, faster to develop liquid fuel rocket engines were exceptionally reliable as well compared to those from those build, test, fix organizations. But there's a big problem with the quality and reliability mindset because that first raw design effort requires more time and more money. And if you have an infant manager who wants the wrong thing fast, well, good luck with that. This is the first hurdle you need to get over. Convincing ourselves that doing it right the first time is going to save us lots of time and money later on. And they say that roughly for every iteration of design, the cost of changes go up by a factor of 10 or an order of magnitude. So the earlier you can get these great ideas into your product, the better. And so that's what they found when it came to understanding the quality and reliability mindset and its effects on liquid fuel rocket engine design and production. Now, I know that probably none of you out there are involved in liquid fuel rocket engine design, and therefore the figures of 73% reduction in costs and 50% reduction in schedule won't directly apply to you, but they're going to be analogous. You would expect to see a large amount of time and money saved when you use the quality and reliability mindset, and the FMEA and FMECA process, when done properly, one of the best ways to incorporate the quality and reliability mindset. Leads us to the next reason, and I touched on this at the very, very start. Amazing products are more than 90% identical to mediocre products. And so if you want that 10% to be associated with your product, how do you get it in there? Well, you need to make sure it gets in there early. It's very hard to have a mediocre product, design, mature, everything else, and somehow redesign it to make it an amazing one where the UI works. It's not going to break or fall apart. Now, AI can really help, like I said, with that very first 90%. So let's look at this concept in action. We're going to examine two, not identical, but functionally identical pumps with the same performance specifications. The yellow pump and the blue pump. Not only are they functionally identical in that they have the same performance specs, their components and the componentry are going to be borderline identical as well. They'll all have bearings and casings and shafts and impellers and seals and lots of other things. And in some cases, pumps from different suppliers might have identical components from suppliers as there are. They might source bearings from the same bearing supplier, for example. Now, it's not uncommon for pumps with the same specifications using the same technology to behave very, very differently. So, for example, the blue pump on the right, it turns out the blue pump on the right is a reliable pump. It just works. The yellow pump, not so much. How is that the case? There may be similar costs. They might have similar components, obviously identical technologies. How is this possible? How can we have these so seemingly identical systems, at least in terms of architecture, have very different characteristics? Well, here's another reason you want to do FMEAs and FMECAs. Around half of all failures occur at interfaces. Now, I've just put a post on LinkedIn which inspired lots of discussion. I think about 90% of comments were all about, yes, I understand that, love it. And about 10% were, well, unless you have a study to demonstrate this, I don't believe it. Well, we've got lots of anecdotal evidence out there. You're never going to have a double-blind peer-reviewed study out there of all failures and all production processes that show about half of all failures occur at interfaces. It's just a rule of thumb that I first learned from Carl Carlson, so I'm not going to claim that this is my statistic. And I've seen in many cases that 50% could be an understatement. So what do I mean by interface failures? Well, for this yellow pump, it could be that there is the common sleeve manufacturing defect which causes leakage. Cooling fans tend to clog, misaligned seal and housing, the gasket isn't properly fit, and it can't handle variation in actual flow rates associated with the user. Now, that common sleeve manufacturing defect causing leakage, why is that an interface problem? Well, if it's a well-known manufacturing defect, and it's going to be something which could reasonably be expected to occur for the components you're going to get, well, the pump manufacturers of reliable pumps design their pump to accommodate that, maybe with some level of redundancy, maybe with some fundamental design which minimizes the effect of that manufacturing defect. If those cooling fins are too close to each other, then unfortunately in some scenarios, they will clog. This happens a lot from my native country, Australia, where we have this talcum powder-like dust we call bull dust out in the outback. And cooling fins, I should say, which work perfectly well in Europe and North America, just seem to catch every single particle there is. And so the cooling fins need to be more spread out when used in Australian climates. Misaligned seal and housing. The seal's fine, the housing's fine, they're just not aligned properly. So here are all examples of reasons why this product might fail, even though every single one of the components are doing exactly what they're supposed to do. So this is a scenario where interface issues, interface failures are destroying the efforts of what could have otherwise been an amazing production effort, where the design team was spot on with specifications and making sure the flow rates were awesome and the impeller shape was optimal. But if you forget about interfaces, then you often produce very unreliable products. Now, AI is very helpful at helping you find those interfaces that you easily overlook. But AI is not great at finding every single interface, which is why we can never leave AI to do it by itself. And when we incorporate these ideas, what's the next thing that happens? Well, our products become better than those of our competitors. And so here's an example based on an industry-leading product, which is the Motorola two-way radio. And the Motorola two-way radio Motorola as a company is an industry leader. Their products dominate the industry, especially in fields like two-way radios, not fields, but market segments that involve two-way radios. And they actually used a FMEA in a very different way outside of what textbooks would suggest to help make this an amazing product. So let's look at how this works. They correctly identified that this push-to-talk button, the humble component, simple switch, is often the most overlooked when it comes to design and operation. And one of the reasons it's overlooked is because it's so simple, but it is also the component with which the user interacts with the most. And that is always going to lead to potential issues. And so what did Motorola do? They first examined their market segment because they realized they wanted to sell their products to military clients who traditionally have struggled to use two-way radios because the operators often have to have big, thick gloves all the time. You simply cannot take a glove off your hand when you're doing military activities. And that is obviously going to lead to some challenges with operating the push-to-talk button. So some designers and manufacturers will say, you need to take your glove off when you're using our product, otherwise it's not our problem. Not Motorola. They defined failure as the push-to-talk button being difficult to press in military gloves. And this is a terrible definition from some perspectives because it's subjective. How do you measure how difficult it is? It doesn't matter if you're trying to inspire good design. So they conducted a FMEA regardless, and they came up with a number of corrective actions. The first one was to improve the textured area to provide better tactile feel with these little rubber nodules, which helped people wearing thick gloves to sense or feel when their thumb was against the button. The second one was to have a colored ring for better visual differentiation. The third and the fourth are my favorites. They added tactile locator ramps in the casing to essentially force the thumb to naturally lie on top of the push-to-talk button. And finally, they conducted a study to identify the optimal activation force and travel for this button for people wearing thick gloves that military servicemen and women would typically use. And so we have these 4 corrective actions when conducting a FMEA for this sort of loose definition of failure. Now, take note of these corrective actions because I'm going to argue, again, in the same way I made the argument for the smart lock, is that those corrective actions are fast, simple, and free if they're part of your first design. If you've gone through the process of designing a two-way radio and someone says, hey, we should add tactile locator ramps to the outer casing, well, that's going to be a lot of rework and a lot of redesign. If you have that idea up front, it costs nothing because you're just defining the first and only shape associated with your case. And so this is one of the reasons Motorola and other companies remain industry leaders, because they're always looking for those fast, simple, and free corrective actions. And that only works if you are trying to look for ways your product cannot work for your user or customer up front. And FMEAs and FMECAs are perhaps the gold standard for doing that. And not only that, if you want to develop use cases for people that you do not understand, AI is incredibly helpful. Engineers often design products that engineers want to use and not customers or users. And so developing use cases and even creating avatars, like images of the person, the fictitious person using the product, can really help the imagination, the brainstorming, and empathy as well. And at the end of the day, if reliability engineering isn't making you money, then you are doing it wrong. And when it comes to Motorola, they are absolutely doing things right. And this tends to be a common scenario for most organizations who do things well. Now, they don't publish these findings too often. Most organizations who do well do not find a need to say, well, this is why we're doing things well, and then publish their findings and results in peer-reviewed articles and journals and the like. This we know about Motorola because they made a presentation to the RAMS a symposium back in 2010 when they described this. And that very rarely do we get an insight, or publicly stated insight, into companies who are doing these things well. And reliability professionals like me and Fred, we can say, yeah, these things happen all the time. We can't talk about them because they're commercial in confidence, or the intellectual property of the organizations we were working with. And so just whenever we have these case studies we can sink our teeth into, you really got to take them and run with them. Which leads us to the next reason to do FMEAs and FMECAs. They eliminate lots of problems. You just saw how FMEAs can eliminate the problem of not having a usable or enjoyable enjoyable. Not having a two-way radio that the military market segment might enjoy. And of course, the military, if they have a choice between a Motorola two-way radio, if those tactile locator amps and all the others that don't, of course they're going to go with the Motorola one because they have eliminated the problems that the customer is finding. But the first problem that we often associate with reliability engineering, problem number one, is the problem in the hands of our user or customer. Now, an issue with focusing on this problem, which we should focus on, is that if you think this is the only problem that reliability engineering for FMEAs and FMECAs address, then reliability engineering never happens strategically. And we'll explain why by looking at problem number two, starting by looking at problem number two, and a problem we identified during manufacture, which is very expensive. Not as expensive as the problem number one. Problem number one is just an absolute disaster. You can rarely recover from it. At least with problem number two, you've got some scope to do something about it before you release. Unfortunately, what usually happens is this term called outlier gets used a lot. When people say, well, that problem we find during manufacturing, unless you prove otherwise, we're going to assume it's an outlier. We hope that's the truth, and hope's not a strategy, so that problem quickly goes back to problem number one. Problem number three are problems identified in design reviews for those organizations doing build, test, fixing, which is expensive and slow. That slows your production process down. Problem number four, a problem we uncovered during initial testing, where we deliberately, in a way, try and torture elements of our system to try and find their weak points. Think about highly accelerated live testing and so on. And these are really cheap. If we know what to look for and we find the weak points of a part of our system, that allows us to not inform the first design, but quickly update designs thereafter. But problem number five is my favorite because that's a problem we never allow to occur in our first design at all. If you think of the analogy of those corrective actions for the smart lock we looked at earlier, that's in a way, these are misnomers because problem number five is a problem we never allow to happen. Now, like I said, many organizations really cannot link reliability engineering to those problems. They don't see reliability engineering as addressing problem number three, which therefore would speed up the production process, trying to get off this build, test, fix treadmill. They don't see that reliability engineering as helping manufacture because we don't need to come and redo stuff we thought was okay. And that means they can't see how reliability reduces budget and schedule if they don't associate those problems with reliability engineering and FMEAs and FMECAs. And so what happens? Well, we only get fixated on problem number one. And this means that reliability is seen to compete with budget and schedule. Because if this is the only problem that FMEAs and FMECAs address, then that is somebody else's problem years from now. That leads to a particular culture where people try to downplay reliability as this is simply delaying their progress to the next milestone. There is no reward for eliminating problems. And there's no incentive either, because if no one else is taking reliability seriously for their components, why should you? Why should you lose all your weekends trying to make your pump that much more reliable if you know the seals and the gaskets and the switches and the PLC will be failing because no one else takes it seriously? So reliability becomes an embuggerance. We test to pass and not test to learn. We continually ask ourselves, what is the least I need to do to move on to the next stage or next milestone? And so you might have some reliability heroes or champions who say, no, we need to do reliability engineering. But in this culture, that relies on business cases because people need to be proven. People need a particular reliability engineering idea to be proven before they spend money on it, as opposed to it being common sense, good engineering. Let's get our fast, simple, free corrective actions in there before we lock our first design in. No, we're going to rush through that, and therefore any change thereafter needs to have a business case. And that brings us back to measuring and not improving reliability, because we have to demonstrate a quantifiable improvement. So we need to measure where we're at and where we're going to go. buckets of gold emerge as opposed to let's just make this right the first time. And our ponderous professor comes back into play because we need the statistics. There's never enough data, and we need to somehow have a business case to convince people that spending $10 today will save $100 later on. And by the time the business case gets approved, if it ever does, well, it's now too expensive to implement the idea anyway. And so we must understand that FMEAs and FMECAs help production. They help us get off the build, test, fix treadmill. As you saw with liquid fuel rocket engines, if we don't rush to build the wrong thing fast, make our first design a reliable one, everything else flows. If you don't believe it, reliability never happens. And from another perspective, you could just say problem number 5 and problem number 1 are essentially the same problem. Only thing that changes is who found out about them and when. So if we look for problems before our first design and design that problem out of our system, it means that problem number 5 is labeled problem number 5 because we did something about it early. If we don't, and our customer identifies this problem, well, now it's a problem number 1. Expensive, unrecoverable, destroys profit and everything else. So although we can never ever forget that our main raison d'etre as reliability engineers is to address problem number 1. From a certain perspective, this is a happy byproduct of doing things smart, optimally, and efficiently by using tools like FMEAs and FMECAs as early as possible in the production process. And leads us to another reason to do FMEAs and FMECAs. It informs testing. Now, remember that liquid fuel rocket engine example case study where certification resources went from here down to here. That's because when you do a FMEA or FMECA, you are not going to remove every possible failure cause from your system. You will know what's left. And that means we're going back to our smart lock. If we're still really concerned about our solder joints, corrective actions we can identify really early are visual inspections of motor solder joints being added to the supplier inspection checklist. Also, we can include a more complex or more detailed inspection if we're still concerned, where we have microscopic optical inspection for 10% of incoming motors. Now that seems like a bit of a mouthful, that last one. That seems like quite an endeavor, and it absolutely is. Why do we do it? We're not there to identify defective components or defective solder joints when you're doing that. What we are trying to identify is the scale of existing defects in those solder joints. Every solder joint will have defects. They become defective once those defects reach a critical size or an allowable threshold. So if we can help monitor the size of the defects that are unavoidable in these solder joints from our supplier, and let's just say our supplier provides solder joints where the typical defect size is really, really small, which is great. If we notice the defect size is starting to increase from really, really small to just really small, well, that's what we call early warning. And if we have a relationship of shared trust and transparency with our suppliers, we can go back to them and say, hey, is something changing with your production processes? Because it looks like the defects are starting to get a little bit bigger. Still within specifications, but let's try and get ahead of this problem. And that means that you will have shared success. If your supplier's success is your success and your success is your supplier's success, by working together, you have both avoided a problem, which from one perspective, from a legalistic perspective, could be entirely owned by the supplier. From an economic perspective, it's shared by both parties. Because if their products become defective and you don't know about it, they're going to cause your smart locks to fail. And so by understanding this and not being too legalistic about it, having suppliers who you want to work with and who want to work with you, you could get ahead of the curve and essentially make sure your products never fail. I've never seen a good outcome where people will essentially say, well, my supplier's job to make things reliable, I'm not going to try and even help them. Why would I do that? I pay them to do that. If it's your job to make it reliable, then you cannot rely on a contract or a purchase order and just hope that everything else works fine, even if they pass those initial qualification tests. And remember, even though it informs testing, you still can't test your way to reliability. You must always make sure your design is reliable from the very, very start. And if you don't do that, then no amount of testing is going to change that. All that testing will do is admire the problems you've created and not eliminate them. Now, AI can help you find the vital few things that you need to test. If everything's important, then nothing's important. And if you don't know how your thing's going to fail, if you've said, well, we've just over-engineered everything, well, how do you verify? You need to get a standard off the shelf or Google a handbook and just say, okay, these 3,000 qualification tests, I guess we're doing all those. That makes everything important, so nothing's important. AI can help you find those vital few things that you need to test. And that leads to my favorite reason, the last reason to do a FMEA or FMECA when done well, is that there is no overwhelm. And when we say no overwhelm, we get rid of this person here, this process zealot. She is the third and final enemy that I will introduce in this conversation. She loves processes and checklists. And the reason why is because she's not an engineer. Even if she is qualified as an engineer, we've met plenty of those people who are qualified as engineers, have a degree in engineering, but they don't know what good engineering does or looks like. They can't look at a hydraulic pump and say that's going to work or not. And so they generate their confidence from complying with the checklist, not because they believe in the checklist, but it creates a defendable position or defensible position for them should something go wrong. They say, well, we did everything in accordance with the standard. The fact that it falls apart, not my problem. I made sure everyone checked the boxes. And that leads to a culture where we have a person who doesn't care how well you do it, as long as you do all things in the checklist, and that is never good. So some of you might have heard of the acronym DFR, and you can see we have this DFR toolbox. DFR stands for Design for Reliability. When we have this checklist approach to reliability, what often happens is all these different tools associated with the checklist somehow need to be incorporated into our production process. And our DFR toolbox is only so big. The amount of tools that people can be competent on and understand is finite, very understandable. And here is but a small smattering of DFR tools that I have found over the years, and they could feasibly be applied in many cases to every single product or system. But that's not good, because now you're doing every single tool that you have some checklist or standard has identified. And I've seen organizations say, well, we're going to take reliability so seriously, we'll do everything. Again, if everything's important, then nothing's important. So this doesn't work. And this is what you see when we have those process zealots running amok in our organization. A complex process, unfortunately, becomes the product. So if you have all these tools, if you have thousands upon thousands of tools, then the process which requires you to use them becomes the product. Hear me out. Why do I say that? Because engineers aren't finished when they design something that's amazing and reliable. They are finished once they've got the final sign-off, once they tick that final box. And so they can rest and relax once the process deems their efforts complete. And if the process is so complex and so overwhelming, that takes all their mental effort, could be over years, to check every box, pass every qualification test. And so they feel complete once the project is signed off. And the more complex the process is, the less the poorer the product is for it. Because complexity should reside in the imagination of the engineer, not the process mandating you do certain things. So when it comes to reliability, if your approach to reliability isn't simple in principle, it's never going to happen. And so if you don't know what tools you need to use, a FMEA and FMECA can really help you do that, find those tools, because those corrective actions can identify if you need to use that tool and not that tool. They can identify if you need to do halt or not halt. And so by prioritizing what matters in a FMEA or FMECA, you get to have a really efficient production process, reliability program, reliability strategy, especially if you don't have one or haven't done one in the past. And so that brings us to AI, our final conversation on AI. This is the standard that applies to AI and FMEAs and FMECAs, even though it is AI guidance on risk management. Why is this relevant to FMEAs and FMECAs? Well, FMEAs and FMECAs are risk management tools by definition. So by definition, you need to comply with this if you work in an organization that is heavily regulated, where you might have safety critical failure modes and mechanisms, where you might hypothetically need to be in a court to defend your product when it comes to liability. Now, if you use AI and you don't know how to incorporate AI and you don't know how to document AI in your FMEAs and FMECAs, then you are done. You simply cannot demonstrate due care when it comes to your FMEA or FMECA. Now, this standard is actually a good standard. It's in principle spot on. It continually asserts that we need to ensure that that humans are in control, not AI. And when it comes to FMEAs and FMECAs, there's some really easy ways of doing that. And so what you never want to do is rely on AI or just rushing through the process, creating that mediocre product, and then trying to have a quality and reliability fairy sprinkle reliability and quality onto this largely finished product, which AI gave you. Doesn't work like that. So in addition to the 10 reasons to do FMEAs and FMECAs, regardless of whether you want to use AI or not, there is some very key things you need to understand when it comes to AI and FMEAs and FMECAs. The very first thing is, if we go back to that diagram I had at the start where we had the quality and reliability mindset, when we insist we have to have this for AI, and then we look at this little diagram here where we have the 90% grey rectangle followed by the final 10% of human imagination. Well, how do we make sure that AI doesn't dominate the human thinking? The very first and easiest thing you can do to make sure that AI doesn't squash that last 10% is by making that last 10% the first 10%. And when I teach FMEAs and FMECAs with AI, we never, ever, 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 ever have AI provide input into a step or an element of a FMEA or a FMECA where humans have not been allowed to brainstorm independently first. That simple act of having people brainstorm before we do AI stuff has time and time again shown to me to be the most effective way of making sure AI doesn't run the show. Humans, what doesn't work is have AI develop a FMEA worksheet or have you, and then have humans try to then mark AI's homework. Humans are terrible at finding holes in things, especially when it comes to line upon line of text saying this failure mode, this and that failure mechanism, this corrective action. It's just too overwhelming visually and mentally to look at a list of ideas and try and identify what is missing. Humans only will do their best work when you start from a clean slate. You get the human brainstorming done first and let AI fill in the gaps or take what the humans have done to the next level. So hopefully that makes sense, and that's how I run. My AI supported FMEAs and FMECAs. So on that note, I do have we do have a question in the chat which I will try and address right now. Okay, who we have here? Carl writes, working together to solve business problem leverages collective expertise, concur, diverse perspectives, concur, and shared resources, concur, to increase efficiency and foster innovation, concur, and reduce risk. I'm still concurring a lot. This collaborative approach often involves cross-functional teams. Absolutely, a FMEA and FMECA involves cross-functional teams. Breaking down department silos to generate creative solutions, improve decision-making, create a stronger, more resilient organisation culture. I do agree. Good engineering delivers reliable, efficient, and secure systems that solve clear user problems, often making complex solutions feel simple and invisible. Balances technical mastery with empathy for the user, proactive problem ownership, and effective communication to deliver business value. Do I agree? I do. We are not finished when we design something that is amazing reliable, because reliability is the floor, not the ceiling of good design. While reliability ensures a product consistently performs as expected, true finished design requires moving beyond more dependability to address your user delight, sustainability, and adaptability. Couldn't agree more. So that's fantastic. Now, Chris writes, does a 50% of failures occurring at interfaces include human system interfaces? And if so, what would the percentage of the 50% would that be? Good question, Chris. The answer is yes, and I don't know, as in the interface issues can occur between the system and the world around it, or between components within the system. There are lots of Martian spacecraft which have impacted the surface of Mars for trivially simple interface issues. The Mars Polar Lander impacted the Martian surface when the extension of the legs were confused by the software as touchdown, and so essentially that meant that the thruster jets, which were supposed to ensure a controlled descent, were turned off when the legs were extended or still attached to the parachute, and it was just simply dropped into oblivion. Its sister aircraft, or sister spacecraft, Mars Orbiter, Mars Climate Orbiter, well, it's either orbiting around the sun in some unknown orbit, or it's burnt up in the Martian atmosphere. The reason being is that when it first approached the Martian atmosphere, it came in too shallow. And they realized when it came in too shallow that the only way it could come in too shallow is if the thruster jets were imparting velocity in a way which was about a factor of 4.45 out. And when you see 4.45, most software engineers know what that means. That's the ratio between momentum in terms of foot-pounds and momentum in terms of Newton meters. So SI versus imperial metrics, which is exactly what happened. One piece of software was outputting momentum in terms of foot-pounds per second, and the other one was Newton meters per second as well. And so that was two interface issues that caused the loss of about $300 million worth of stuff. And then, of course, you have the interface issues between the system and the world around it. And that can often mean that the system is seen as a subsystem to other subsystems, but aircraft in particular. Lots of pilot error have been associated with poorly designed cockpits. An example is Air France flight, forget the number, which impacted the Atlantic Ocean. One of the issues there was essentially, as opposed to having a control yoke between the legs of the pilots, would also push forward and back so they knew what was going on. In this case, it was the first officer on the right that he had a joystick on the right-hand side. It was dark, and the joystick is supposed to do all this stuff. And the co-pilot on the left, he had a joystick on his left. And you can't see what the other ones are doing, and when they're not mechanically connected. So essentially, the first officer was pulling back, the co-pilot was pushing forward, the plane was confused, and it was essentially still climbing with the nose pointing up in the air, stalled and impacted the Atlantic Ocean. Lots of examples of interface issues between the system and the user, and then the components within the system. And no, I don't know what the rule of thumb breakdown is regarding system and environment versus component and component interface issues. That's a long-winded answer where I essentially say, Chris, I don't know. So apologies for that. But hopefully it's a good story. So before I close up this conversation, if there's any more questions, feel free to ask them. But I will say, I often start this conversation by saying, I have 10 reasons to do FMEAs and FMECAs. And I know a lot of you might have thousands of reasons to not do them because you've had bad experiences. So I want to finish off this conversation by saying there's a world of difference between a good FMEA/FMECA and a bad FMEA/FMECA. Good FMEAs and FMECAs focus on doing part of the system well. Bad FMEAs and FMECAs focus on doing all of the system poorly, where you have this pressure to try and identify every conceivable failure mode and mechanism before you start designing. That's not possible. It's simply not possible. And some FMECAs where they demand failure rate estimates as well, it turns this, what's supposed to be an illuminating discussion on prioritizing effort, into this exhaustive spreadsheet building, failure rate researching, a breakdown of potential ways a thing can fail. And what that does is that sucks the oxygen from the room when it comes to reliability engineering. If you've ever been part of that sort of FMEA or FMECA, and I certainly have, you don't want to do any more reliability engineering ever again. You've spent a week or 2 weeks doing that hell on earth, and you have precious little tolerance for a reliability engineer to say, hey, we need to do this. So FMEAs and FMECAs, one done well, focus on the vital few. The most important output of those activities are corrective actions, not failure rates, not SOD. They can come later if you need to fine tune them, but it's identifying those fast, simple, free corrective actions up front and not trying to measure every single possible way an undesigned machine, product, or system can fail before you start designing it. By definition, that's impossible, and we don't want to do that. So before I open it to any more questions, sorry, are there any questions before I finish things off for today? Thank you, Carl. You guys just want me to stop talking that bad. You don't have any further questions, which is fair enough. I respect that. Thank you, Chris. No worries, team. Thank you, Michael and Arjun. I don't think there's any more questions coming, Fred. Could be wrong.
All right. Thanks, Chris. We'll wrap it up there.
No worries. If you do have any questions, you got my contact details, Fred's contact details. I mean, there's a lot of stuff on Ashendo from Carl, who's I was about to say he's the FMEA guru, but his correct term now is retired FMEA guru. Is that about right, Fred?
Yeah, I think so. He still answers questions, though.
Absolutely. He's addicted to FMEAs. He can't help himself, so he's just not doing as much traveling these days. All right, team. And sorry, last but not least, I do have a practical FMEA and FMECA course which I've just launched. If anyone's interested, there's an Ashendo discount. You can just reach out to. You can just have a look at some of the newsletters that Fred has released. There's the discount code, and it'll be launched on the 23rd of Feb. If you enroll early, there's a discount, and if you use the Ashendo discount as well, you get even more of a discount. And of course, there's group discounts as well. So if you're interested in doing FMEAs and FMECAs, and you want to see how we can use AI to help take existing FMEA and FMECA processes to the next level while saving time, please feel free to check out the course.